Assalamualaikum and a very good afternoon, ladies and gentlemen. It is my great pleasure to welcome you to the first Malaysia International Conference on Nanotechnology and Catalysis (MICNC 2021). We are now in the sessions of Technical Talk and Keynote Session 6. My name is Yasmin Abdul Wahab from NanoCat and I will be your session chair for this afternoon. For those who intend to ask questions to our honorable speakers, you can channel your question in the chat box and your question will be raised in the question banner and will be highlighted accordingly. So to start with, I am honored to give a brief introductions of our first speaker for our technical talk, Dr. A.B. Su from High-Tech Instruments Sdn Bhd. AB received her Bachelor of Engineering with Honours degree from University of Malaya, and Master of Science degree in Materials Engineering from University Science Malaysia. AB continued her research at the University of Queensland, Australia, and obtained her PhD degree in Materials Engineering in 2017. She optimized the growth of different types of 3,5 nanowires using MOCVD and applied different analysis techniques in EM such as TEM, STEM, EDX, CBED, EELS, as well as CS Corrector stem to study the growth mechanism of those 1D nanomaterials. Between the year 2015 to 2017, she was a staff member at the Center for Microscopy and Microanalysis, CMM, University of Queensland to provide analytical TEM training for the researchers from both academic and industry. In 2018, she joined High-Tech Instruments as a technical PA and application specialist to oversee various projects and provide technical solution, especially in the area of advanced imaging and characterization for the customers. So without further ado, I would like and I am honored to invite Dr. A.B. Su to share the technical talk on Hitachi SF5000 in situ observations of catalytic particles in gas atmosphere using aberration-corrected scanning transmissions electron microscopy. Welcome. The stage is yours, Dr. AB.
Thank you, Chairman, for the introduction. Hi everyone. I'm Dr. AB here from High-Tech Instruments. Today is my honor to share with you some of the latest technology by Hitachi, which is the invention of the CS Corrector STEM, TEM or SEM. The model is SF5000 with the in-situ observation of catalytic particles in gas atmosphere using an aberration corrector scanning transmission electron microscope. So it means that this STEM or the TEM itself, you can do in situ observation of your catalytic particles, and you can inject the gas to see the reaction of the catalyst. And a little bit of the overview of this development of next generation 200 kV field emission TEM. So TEM and STEM, TEM transmission electron microscope or scanning transmission electron microscope market segments predicts the largest growth in the coming years. STEM market has been growing significantly since 2009, so it's almost more than 10 years now. And it's actually like 4 or 5 years. And academia, researchers in the academic and semiconductor industry, the requirement is that to have the high resolution imaging and also to have high sensitivity elemental analysis in this field emission TEM or STEM. And today the focus is actually on the catalyst research, such as fuel cell, is increasing in demand for in situ imaging in the gas atmosphere. So that's the outlook of the Hitachi SF5000, and a little bit of that. So what is the requirements for the atomic resolution, observation, and analysis? It means that your sample you put in, not only looking at the small particle, nanoparticles, but you can observe the atoms within your sample, your particles. And we know that the atoms is actually the arrangement of the atom, the crystal structure is actually greatly affecting the performance of your catalyst particles. Yeah. So for functional materials development, failure analysis, and so on for the industry semiconductor, we actually require for the development of the TEM stem, high stability and throughput capability is required. And high resolution and sensitivity is very important. And also very one thing to emphasize is that this equipment is to allow versatile observation, such as you can observe TEM, the STEM, and also SEM in one system. And it comes with the CS Corrector automated alignment for the usability improvement to achieve atomic resolution. And also you need to have the high stability of the electronics and mechanical of the system so that it reduce or minimize the vibration when you capture atomic resolution imaging. And also it's very important to have low specimen beam damage on your sample. And ease of use is something very important for the user to operate this dedicated atomic resolution stem. So with these requirements, Hitachi is actually developed this next generation 200 kV fuel emission TEM or STEM. Come with a high brightness co-FE gun, which provides a very high resolution and stability of the gun itself. And it comes with a fully automatic aberration correction function developed by Hitachi, and high sensitivity elemental analysis by high solid angle, the SDD detector, and simultaneous observation of the surface by the SE detector, and the inner structure in a variety gas atmosphere, this one by STEM detector. And this one you can actually induce a gas. And that is the requirements for high resolution and sensitive analysis for wide range specimens, and integrating the technologies into this model, HF5000. So require high the field emission, transmission electron microscope, scanning transmission electron microscope, or scanning electron microscope, 3-in-1 in a system. It can achieve the high resolution analytical capability in TEM, STEM, and SEM. And also it comes with the design of the environmental imaging. We call it eSTEM or ETM or eSEM. So this is an in situ lab in gap, and it's actually designed with the ease of use. And this one is actually for the stability of the system itself. So a little bit of introduction is this one. It comes with the Hitachi fully automated prop-forming spherical aberration corrector for the atomic resolution imaging, and it has the high brightness and stability co-FE electron gun, and ultra stable column, and power supplies for management, and it can do simultaneous CS correctors SEM and STEM imaging capability with atomic resolution. And it has a new high stability side entry specimen stage, and specimen holder is actually covered by this box. And you can have this symmetrically opposed dual 100 square EDS detectors, and the new design enclosure for optimum performance in real lab environments. And there is a wide range of Hitachi advanced specimen holders, different kind of specimen holders you can use in this lab in gap design, and lab in gap capabilities gas injection and differential pumping for environmental TEM and environmental STEM. So this is actually the similar things. And the design for this, to highlight that, the design of this in situ lab in gap is focused on the catalyst analysis experiments. So in worldwide, there's been the model of HF5000 that been installed in different research center and also industry focused on the catalyst activities, or their research focused on the fuel cell catalyst. And there's the specification here. I'll just highlight it's that the TM resolution is 0.1 102 nanometer, and that is the different tilting range. So yep, and this is how the auto alignment Hitachi in-house CS corrector can be done. So it's actually by just one click. You see that even like an atom here for this sample is a silicon sample. For without CS corrector, you only can see this one thing, but with the CS corrector and with this ease of use single alignment by one click, you can resolve the two atoms within one lattice. So this is how it is after correction. And this one also to highlight that the fast and stable of switch between different mode. So this is the control panel of the SF5000, and this is the STEM imaging, the dark field STEM imaging. Is also atomic resolution. You switch to TEM by just one click, and you switch back to STEM. It's a very simple clicking and switching. And this is the TEM image window. You have the image and all the operation. And this is the FFT. If let's say you have the adjust the stigmatism or the lattice, you can see from the FFT image, fast Fourier transform. And for this one is you can, it's actually for this model, you will simultaneously display 6 channel STEM window. This is a SE imaging, bright field imaging, dark field imaging with their corresponding FFT images. Yep. And the simultaneous atomic resolution of STEM SEM imaging and movie recording is available for especially when you want to see the activities of the catalyst reaction when you in the lab ingot setting. So dark field STEM showing your Z contrast with the material contrast. So the bright one is actually showing higher atomic number, and the bright field STEM itself is actually showing phase contrast. So it's all in, it's a platinum, it's a gold nanoparticles. Yeah, you can see the atom here. Even with the SE imaging is something very special with to install in a TEM, the detector. It can also achieve the atomic resolution SE imaging. It means that these two, you are looking into internal structure of the gold particle. This one, you're actually looking at the surface of the nanoparticles. Later, we'll have some example to explain to the audience, like why it's important to correlate these two the results. And that's the detector configuration here with the CS corrector. And this is the SE or BSE detector here. So that is the corresponding SE imaging. There is a catalytic particle on the support, carbon support. And this the dark field detector here. And you have the bright field detector here. Your specimen is here. So this is your the same location. You can capture the images simultaneously. So you see that for the same area, same location. For the SE imaging, and the hard diff or the ADF STEM imaging, dark field imaging, you will see different information from your sample. And the next one, this one is actually, you also can do direct observation of oxygen atoms, which is something very significant, is to observe oxygen atoms using your bright field STEM detector. Dark field STEM you can't observe, but for this one, when you enlarge that, you can see the oxygen atom here. These are all atoms. Yeah. And the next thing is about the EDX detector. Usually for the configuration of TEM, you only have one TEM detector. But with this design that with a high sensitivity, dual STD detector is actually achievable. And with this double detector, with 200 square windows and windowless STD detector, you actually it offers you double count rate of your EDX analysis or mapping, and it is less specimen tilt angle sensitivity. It means that no matter how you tilt your sample, your count is always at the maximum. So this one positive tilt, 10 degree, this one negative tilt. And the automated protection retract of STD when large electron induced. Yeah, this has come as a. So this one is one of the example of the EDS mapping at atomic resolution. So this is gallium K alpha is a gallium atom here. You view along 110 direction, and this one is arsenic, and this one is the kind of the mapping of these two. So you have the gallium atom here, the arsenic atom here. It's very nice mapping using this the dual detector here. You can map even for atomic resolution. And for this one is another example of the strontium titanium oxide. So this is the dark field STEM. This is the SE imaging. You can see that this one showing that it's like have the carbon on top of the sample, because this one gives you the surface imaging, and you also can have the atomic resolution on your SE and for your dark field stem. And this is the EDX atomic column mapping. So all the atom can be accurate and nicely mapped, even for the oxygen here. So yeah, that is the what's that, the modeling for the strontium titanium oxide view along 100. So it match exactly with your experiment data and your theoretical modeling. And the next one is another example for the use. Yeah, and I would go like this one, introduce on the in situ capability. So the previous is all those capability within the HF5000, and how this in situ capability can be we can have that in the HF5000. Come in the introduce a background, the in situ microscope and result, and some application. So in order to understand the reaction characteristic of catalyst, there is an increasing need for microstructure evaluation in real environments using TEM or STEM. And catalyst, which is also the particle size has become smaller, and you realize that it really becomes smaller, which offer the excellent performance such as metal nanoparticles, clusters, or even single atoms. And in situ observation is required to have a higher resolution than before. So for the design of this environmental stem in HF5000, it comes with a gas injection and envelope the sample heating using the holder, and also the aberration corrector stem to achieve the atomic resolution. And that is this is the traditional closed window. So this is a column, and usually the holder is actually entrapped here to have the gas flow within the holder. And there's a membrane here. You put your sample here, but this whole column still within high vacuum. And the pressure for this one is actually 10 to the power of 5 Pascal based on the column, TEM column pressure. And the resolution somehow is limited due to the beam scattering of the membrane, because there is membrane here, so that the gas won't release to the high vacuum here. But for with this open window in this HF5000 design, the pressure is actually you can achieve. You see that now your holder is actually no longer limited. You actually your gas directly injected into the TM into stem, but with this orifice here to protect the chamber at your cold FE. And the pressure here you can achieve 10 to the power of 3 Pascal. The resolution now you can achieve atomic level. And the advantages for this one is your SE images also can be captured with the detector, and you can achieve higher spatial resolution, and also the EDS detection sensitivity. So this is the background of the design of the lab in-gap in HF5000 for the catalysis observation. So yeah, for the open window here, so that you can see the gas system here. So this is the nozzle here. You can inject the gas nozzle, gas into using the column nozzle here onto your sample. And you have this holder. Any holder can work now. So this holder depends on what kind of experiment you want to do. You insert the holder, and this one is actually heating holder. So the gas can be locally injected to the sample, nitrogen or air, or even this kind of gases, depends on your experiments. And the estimated pressure around the specimen is 10 Pascal at maximum gas flow. So you can adjust the gas flow here. And yeah, there is a dispersion pumping aperture here. So to pump this area to have a good vacuum. Yet this area you can have different gases to inject into this specimen holder here. Okay, and the next one, I think, yeah, that is another, is actually controlled by the software. You can actually click on your gas is into the holder or to the nozzle. So like the gas flow, everything all controlled by the software. And yep. So this one, the whole thing is to highlight that even with the in situ experiment, it won't affect the basic specification of your of this HF5000. Like your lattice, the stem resolution is 78 picometer. When you do in situ with a gas induced, you still can achieve 78 picometer for the atomic resolution imaging. All remain the same because of the lab in-gap design. And this open window allows user to have the insert different kind of like specimen holders, and you can observe the STEM and SEM, and you have the sensitivity extract analysis. So that is how the setup. And I think due to time, that is the different holder here. I will share with you some of the experiment data here. So this one basically is using the heating specimen holder here. Your sample is actually on top. You place on top of the silicon nitride support film, and there's a heating holder here. So maximum temperature is 1100 degrees Celsius. So this one is the SEM imaging here. This one is dark field. This one is before the reaction. Before I heat the sample, is the platinum carbon catalyst support on the carbon. Want to observe the catalyst deterioration. So these platinum particles here is supported on the carbon. So this one is still on at the high vacuum, and after air induced into the chamber, you can see that and heating up to 350 degrees Celsius, you can observe the deterioration of the catalyst itself. The platinum itself is actually kind of like diffused into the carbon support when you observe this SE imaging, that the morphology, and it entered up in the porous surface of the carbon support, and the platinum disappear. And if you observe this STEM imaging, it's actually all this particle has been diffused into the catalyst. And this one also, the dark field STEM also show that the platinum particles has been coalescent, like kind of like agglomerate together with during the heating, and also when the air induced into the specimen during the reaction. So this is to show that at this different environment, at heating at 150 degrees Celsius and in nitrogen environment, and even increase to 300 degrees Celsius, the atomic resolution can be achieved. It doesn't affected by the gas that you have been induced, and also the heat that you induce on your sample. So the next one, yeah, is a quick video. So to show you the you can capture video. So this is dark field STEM. You can see this one agglomerate, and this one is showing the activities on the surface. And slowly you can see that all this diffuse into the carbon support itself, and it will disappear in your SE imaging because it's only uh, um, SE imaging collecting the surface morphology. So slowly it disappear here, but you still can observe in your STEM, because STEM observe the internal structure. It penetrates through your sample. So it's very important to have this correlate results for your catalyst observation. It's very nice video here to show the movement of the platinum catalyst. Yep. So this video is actually 9 minute total, but it's actually kind of like compressed that into 56 seconds. Yeah, we even like the current is actually okay. And I think there are actually more example here on the correlative, the catalyst particles here. You can see that the platinum here up to 400 degrees Celsius is actually diffused towards the carbon, and is very good lab in-depth design to view using your own eyes on how the catalyst affected by the heating, and also the gas environment. It's not only like after that only you observe the result, that you have to kind of like go and like think of like what actually happened during the whole process. And that's a more example here, and this is, yeah, but I think like to come to this is the real particles here in the nitrogen, and also the high vacuum, to show the capability of the atomic resolution. So the conclusion that I will make for this very quick introduction of this H5000 and in situ capability here is that Hitachi 200 kV field emission TEM, STEM, and SEM provide atomic resolution imaging and various type of analytical capability in ease of use. And also, it combines the technology that enables atomically resolved surface morphology information by SEM, which you observed in the video just now, and also the material information, the Z contrast or the phase contrast by the STEM, bright field or dark field STEM detector, with a stable cold field emission source, and also the automated aberration correction to observe the atomic resolution as well as very high sensitive EDX analysis. And also with this in situ option adopted into the system, most of the specifications still remain the same. You can achieve the best quality, even you have the in situ experiment. So with the in situ capability and the capability of the HF5000 itself, it provides the real active substance under real reactions, a catalyst of activation. We call it lab in gap. So your lab here is a real lab within the gap. Yep. So I will end my presentation here, and thank you so much, and welcome with questions from the floor. Yep.
Thank you so much, Dr. AB, for addressing the interesting technical talk on Hitachi HF5000 for in situ observation using your corrected stem. So, ladies and gentlemen, now we come to the Q&A session. So, the first question is from Ms. Lina Al-Nani. Thanks, Dr. AB, for the interesting technical insights. Is it possible to analyze tissue sample cells treated with nanomaterials after it being processed with microtome for TEM by HF5000, TEM, STEM, and SEM? Thank you.
Yes, this is thank you for your questions. For the TN itself, is actually the basically the capability it can achieve that, because for this HF5000, sometimes for your sample, if let's say beam sensitive, if 200 kV somehow is too high for your sample, you can reduce the kV to 80 or 60. So the short answer is yes, can analyze your sample. Yep.
Okay, thank you, Dr. AB. Thank you so much for your answers. So, there's one more question from Dr. Nor Alia. So, dear Dr. AB Su, thank you for your great sharing. Does this SEM version can come with the EDX analysis?
Oh yes, definitely yes. The EDS analysis is actually either you can have the single detector or the dual detector. But in order to get a very good atomic resolution, we suggest for the double detector here, the dual detector. So that is one of the results that with the atomic resolution EDS mapping. Yes.
Okay. All right. Thank you, Dr. AB. So,
Welcome.
with that, I would like to thank you, Dr. AB Su, for your fruitful sharing and participations in this MICNC 2021 technical talk. So now we're going to moving along to our last keynote speaker for MICNC 2021. I am pleased to give a brief introduction of our Professor Dr. Azhar Arifin from University of Malaya. Professor Dr. Azhar Arifin obtained his PhD from University of Nottingham in Asymmetry Organic Synthesis. After graduation in 1999, he returned to Malaysia and joined Chemistry Department, University Malaya, working as a young lecturer. In 2003, he was promoted as an associate professor, then to a full professor in 2016. So in his research interest is actually mainly focused on the organic synthesis. And currently he has two research projects, which is one is on the synthesis of quinozoline derivative as anti-cancer agents, and the other one will be on the synthesis of carbazole derivative for applications in OLED. So without further ado, I am honored to invite Professor Dr. Azhar Arifin to share his keynote speech on the carbazole-based dendrimers in organic light-emitting diodes OLED applications. The stage is yours, Prof. Dr. Azhar. Please welcome.
Okay. Assalamualaikum and good morning, everybody. Good afternoon, everybody. Thank you, Mrs. Chairman. First of all, I would like to thank the organizing committee for giving me this opportunity. First, can you see my slide?
Yes, we can see.
Okay, so the title of my talk today is about carbazole-based dendrimers in organic light emitting diode application. As Mr. Chairman told, my name is Azhar Arifin and I'm currently working at the Chemistry Department, Faculty of Science, University of Malaya. So what I'm going to share with all of you today is some research that we've been doing for the last 10 years related to this OLED application. So before I go into further detail about my talk, let us look a little bit at a history of what we are using today. So this is some history about myself as well. This is my first handphone that I bought after I finished my PhD in 1999. This handphone was introduced to the market in 2000, if I'm not mistaken. And then this, what we call it in Malaysia, I think they used to make a joke, is Nokia 33 Skupang ataupun Nokia 3310. So this first handphone that I own is using LCD display. Then it was first in the market in 2000. And then now this is my latest handphone that I have, which is Samsung Galaxy Note 9. So this handphone using the screen is Super AMOLED display. So I'm very sure most of us today is using this kind of smartphone. So if you have this smartphone, so I'm sure that you have heard about the word OLED before. Okay, so because the latest technology in the smartphone are using AMOLED, for example, the Samsung versions of handphone, they're mostly using Super AMOLED for their display. So this is what I'm going to share today, but not going to share the technology of making this OLED display, but I will look at the very fundamental aspect of the material that is used in making this OLED display. This OLED research was first come to the attention to the researcher in 1987 when these two guys, Stephen Wenslide and Ching Wan Tang, published an articles in Applied Physics Letters under the title Organic Electroluminescence Diode. So since then, a lot of research has been conducted on this research, but only after 10 years later, which is in 1997, the first OLED display was introduced to the market, which by a company called Pioneer. And then in 2003, if I'm not mistaken, the first digital camera that using OLED display was introduced to the market. So just to basic introduction for those who did not know what is OLED is all about. So OLED stand for Organic Light Emitting Diode. So that is the short form for OLED. The full name of OLED, Organic Light Emitting Diode. So from the name, you know that the material that is used to make this is organic material. It is a thin film display technology that contains an organic material which emit light when current is passed through. And it is mostly used in digital display, for example, your smartphone. And also now it's been used widely as a solid state lighting application. And also now you can also buy a laptop that using the display is made of an OLED material. In the market today, there are two types of OLED that is available. One of the OLED that is available, we call it passive matrix OLEDs, or well known as PM OLED. So this passive matrix OLED is using a simple control scheme in which each row in the display is controlled sequentially, and this kind of PM OLED mostly you can find in the device that is smaller than 3 inches. For example, I think nowadays people are wearing this kind of smart watch or health digital on their hands. So mostly of this kind of gadget are using this passive matrix OLED technology for the screen. And the second type of OLED is called active matrix OLED, or in short, they call it AMOLED. So these AMOLED are widely used in a smartphone. Okay, most of our smartphone are using this AMOLED technology. If for Samsung, for example, they call it Super AMOLED. And then this is an example, the schematic diagram, simple schematic diagram, the difference between PM OLED and also AMOLED. So on the left hand side here is a schematic diagram for the passive matrix OLED, how it works. And then on the right hand side is an example of the active matrix OLED for those who want to know in detail. So they can this is how your digital display is made of and how it works. In general, most of the OLED device have 5 layer basically. Okay, the most common OLED structure generally consists of 5 functional layers, which is include whole injection layer. Okay, this ITO is the anode, and then after that we have this whole injection layer that will carry the positive charge, and then after that we pass to this whole transport layer, and then from whole transport layer the positive charge will pass to this emissive layer, EML. And then from the cathode side, which is normally an aluminum, we have the electron injection layer. Okay, this layer is will pass the electron, and then this electron injection layer then pass the electron to electron transport layer, and then from this electron transport layer, this electron will pass to this electron emissive layer here. So when this hole and electron mix together at this yellow box here, then the light will be emitted. So that is how this basic OLED display is working. So these all 5 layers are made of organic material, and they are sandwiched between 2 electrodes, usually reducing metal cathode and a transparent oxide anode. So how do OLED work? So before we look at the OLED, because OLED come after LED, so might as well we just look first at the LED, how LED works. So when you know how LED work, then we can easily understand how OLED work, because these two LED and OLED are interrelated in each other. So LED are electronic components that are used as small color indicators. Then this LED will produce light, okay, when photon of light are emitted due to the electron movement in the doped semiconductor. So this is how we get light from the LED device. Whereas the organic LED is actually simply a variant of this LED, in which in the OLED, the light is emitted by the organic molecule. So in the LED, the light is emitted by this doped semiconductor, which is normally metal like gallium. Okay, and then there is many other metal that being used as the semiconductor here that will emit light when electron and the hole are mixed together at this position here. So that is for LED. And then for the OLED, we just replace that metal with the organic molecule, as I mentioned in the previous slide. Okay, we have 5 layers of organic material, and each of that 5 layers have their own roles. So to bring the hole and electron together into this green box here, and then it will emit light when everything is in order. Okay, so that is how OLED work and how it different from the LED. If you look in the market today, one of the report mentioned that the global OLED market size was valued at US$38.4 billion this year, and it is projected to reach US dollars 72.8 billion by the year 2026. And it is expected to grow at a compound annual growth rate of 13.6% during the forecast period. So this is, you can see how big is the market of this OLED business. Okay, for this year alone, is the market value is 38.4 billion and it's predicted to increase to 72.8 billion by the year 2030. So it's a huge business here and also huge big opportunity for us to do research in this OLED kind of technology. However, there are many challenges in the OLED research in the effort to produce a good OLED device. One of the many challenges that facing in this OLED research is how to design and synthesis organic molecule that suitable as host material or as any layer in this OLED device, because in the OLED device most of the components are made of organic material. So one of the many challenges that is facing is how we can design an organic molecule that fulfill the characteristic to be a good material as an OLED. Because for the molecule to be good OLED, it have to have triplet exciton confinement, because this triplet exciton confinement is the prerequisite for efficient phosphorescent organic light. And then one of the way how to achieve this triplet exciton confinement is by incorporating meso, insulating or twisted configuration into the molecular design. So there is some kind of structure of the organic molecule that we have to make in order to achieve a characteristic that's suitable for the OLED. And then not only that, the molecule that we synthesize, especially for the host, it should have triplet energy higher than the emitter. So in the OLED device, we have host, we have emitter. So the host must have triplet energy higher than emitter in order to prevent energy back transfer from the phosphorescent gas to the host. And then another criteria is the molecule should have high glass transition temperature, ideally more than 100 degrees Celsius. And then if possible, okay, the molecule should be solution processable. So if solution processable, then we can make a big device. But there are other techniques also available like vacuum deposition, but it depends on the capability of the research group. If they have the facility for solution process, the spin coating technique, maybe vacuum deposition, maybe they can use a lot of things. But if like us, we don't have that vacuum deposition technique, we rely on this solution processable. So we have to synthesize the molecule into a big size, then only it can be solution processable. So in my research, we are focusing on this design and synthesis of the organic molecule that is suitable as a OLED candidate. So we choose carbazole as our structure or framework in our research. So this is the structure of a carbazole. So carbazole is actually a polycyclic aromatic hydrocarbon that contains two 6-membered rings fused to a 5-membered nitrogen containing. So you can see here we have two benzene ring and fused into this 5-membered ring of a nitrogen containing 5-membered ring here. And then if you look carefully, this carbazole is actually half of the framework is come from this indole. Okay, and then this carbazole also is a isoelectronic to this fluorine here. So the difference between carbazole and fluorine is that we replace the CH2 group here. Okay, we have CH2 group here with this NH group here. So this carbazole is actually isoelectronic to this fluorine. Okay, other than carbazole, we can also have this indolocarbazole. Okay, this indolocarbazole, you can have the nitrogen facing opposite to each other, or you can have nitrogen facing to each other. So these two structure also have a good properties for the making an OLED device. Okay. So this is the structure of the carbazole. So this is the basic structure of the carbazole, and then you can make this indolocarbazole like this one and this one as well. So why we choose carbazole as the substrate in our study? So one of the reason is carbazole has high triplet energy. So in the OLED, making an OLED device, in order to make it a good material for the OLED, the material should have high triplet energy. Okay, and then how to get the high triplet energy? The molecule should have short conjugation in the molecule. So this is what the carbazole have. If you look at this diagram here, you can see these two aromatic ring here. These are high aromaticity. And then these two high aromaticity is separated by this reduced aromaticity of the 5-membered ring nitrogen containing compound. So by having this kind of structure, so we have this property short conjugation. So that is why carbazole has a high triplet energy that is needed for a good OLED molecule. And on top of that, carbazole also is an excellent hole transporting, has excellent hole transporting material where the HOMO level is around minus 5.0 electron volt. And then this is another property that we can have a torsional angle when you introduce a substituent at position 3 and 6 here. And then this aromaticity of the carbazole give the stability to the molecule that we synthesize. So this is in terms of the electronic properties of the carbazole, why carbazole are good as a organic molecule as candidate for the to make an OLED device. In terms of chemical properties, why carbazole is interesting? Because this carbazole, you can do direct substitution at position 3 and 6 here. And you can do indirect substitution at position 2 and 7 in order to get various different kind of structure to make that molecule suitable for OLED device. So for example, here you can easily do Friedel-Crafts acylation. Right, this is just undergraduate chemistry. I think most of you who take organic chemistry should know this reaction. You can easily do Friedel-Crafts acylation or acylation. Then it will go substitution at position 3 and 6 using aluminum trichloride as the Lewis acid. You can also easily doing this Friedel-Crafts alkylation. Okay, you just replace this acid chloride with this tertiary butyl chloride. You can use either aluminum trichloride, or you can use zinc chloride also in order to introduce this tertiary butyl group on the position 3 and 6. You can also easily do halogenation at position 3 and 6 by using N-chlorosuccinimide or N-bromosuccinimide or N-iodosuccinimide in solvent DCM, the chloromethane. Then you can easily introduce halogen at position 3 and 6 here. Okay. Whereas for substitution at position 2 and 7, you can also do that, but slightly difficult from position 3 and 6 because this is, you have to do indirectly. For example, here, okay, you have to start from this meta-substituted aniline, react with this meta-substituted halobenzene here using Ullmann coupling reaction or maybe Buchwald-Hartwig reaction. You get this bisphenylamine, and then this bisphenylamine, you can do oxidative cyclization at these two positions here. So you will get this 2,7 substituted carbazole. For example, here, if you want to synthesize this 2,7 difluorocarbazole, you can start with this metafluoroaniline. You react with this metafluorobromobenzene. Under Ullmann coupling reaction or Buchwald-Hartwig reaction, you get this bisphenylamine here. And then in the presence of palladium acetate as a catalyst here, you can do oxidative cyclization. then you will get this 2,7-difluorocarbazole. You can also introduce a different substituent at position 2 and 7 by changing the starting material here. For example, if you use a meta-methoxyaniline, you react with this meta-bromo-N,N-dimethyl aniline here. Okay, it will form this bisphenylamine first. And then again, you do oxidative cyclization by a catalytic amount of palladium acetate. Then you will get this 2,7-disubstituted carbazole. Okay, why we want to put all these substituents here? Because these substituents have their role in making this molecule as a good candidate for the OLED device. Okay, because by doing this, you can make this carbazole become a good donor. Okay, and then if you attach to a good acceptor, then you can make this molecule become a good candidate for the TADF, what we call it, thermally activated delayed fluorescent. So that is one of the thing that you need to know when you dealing with this OLED device. And then lastly, about the chemical properties of the carbazole is we can easily form a dendrimer like this on the carbazole. Okay, after you do substitution at position 3 and 6, and you do halogenation at position 3 and 6, you can couple these two carbazole here with each other, either using Ullmann coupling reaction, or you can use Buchwald-Hartwig reaction. So you just need to change the reagent here. If you want to use Ullmann coupling reaction, so you just use copper in the presence of copper oxide, or sometimes you can use copper iodide, but you need high boiling point solvent, for example, like dichlorobenzene, because this reaction require high temperature. For the Ullmann reaction, then you can get this dendrimer here. Okay. If you want to know more example of carbazole-based organic compound for the OLED application, you can look in this publication here. Was published in 2017 by Dr. Bridget Wax and Professor Dr. Bilal Kafarani. Okay, so in this review paper, you can see a lot of organic compound contain carbazole moiety that have been used in the study of the OLED. So in this case, particularly referring to the emitters layer and also the TADF properties of the OLED. Okay, so this is just one example of the carbazole that carbazole dendrimers in this OLED study. This molecule was synthesized by Professor Wang. It was published in 2014. This molecule actually in 2014 scared us because at the same time, one of my PhD students also working on this kind of molecules. But we just lucky that we don't have the tertiary butyl group, so we use tertiary pentyl group, so we get the same molecule but with different substituent at this position. But what I'm trying to say here, this is one example of the carbazole dendrimers that have been proved to be good as a OLED candidate. So our research start from this molecule here when my friend from physics, Dr. Woon Kai-Lin, designed this molecule by computational, and he said this molecule probably a good electron transport layer. So then he designed more molecule as shown here. So this is our design compound, and we have patented it. Okay, so due to the time constraint, I will not discuss all this molecule. I will maybe just show one example how we synthesize this compound 2.0 and what is the problem that is facing during synthesis of this molecule here. All these molecule actually only designed, but at the end we have to synthesize something else due to the problem that we face. So first we look at this compound number 2 here. So this compound number 2 can be easily synthesized starting from this compound. That what we thought initially. So we had this in the lab, so we just try do iodination and then Ulmer coupling reaction. But unfortunately, this reaction didn't work very well. We get multiple products. And then the intended product here, we get only in 5%, which is very, very low in the organic synthesis point of view. And not only that, we also discovered that this compound have solubility issue. So it's not suitable for solution processable. So due to that, we have to modify the structure, how to make this molecule solution processable. So we decide that maybe if we add in alkyl group at the carbazole here like this, then maybe it could solve this solution processable issue. So that's what we did. So we modified our dendrimers. So we synthesize this dendrimer here. So this is the pathway. Those who interested maybe can look at the slide later on how we synthesis this dendrimer in order to overcome the problem of solubility. So after we get the dendrimer, then we do Ullmann coupling reaction with various acceptor or various linker here. We have for compound 2, we use this 1,4-dibromobenzene. We also have this diiodobenzene. So we have this 1,3-diiodobenzene. We also have this kind of diiodo biphenyl compound here. So we have successfully synthesis 4 different compound here using the Ullmann coupling reaction by this dendrimer. And then we get compound 2.1 here, compound 3.1 here, and then compound 4.1 and compound 5.1. So if you look carefully at the structure here, this compound looks similar to the compound published by Professor Wang in 2014, but we just lucky that we did not use the tertiary group. Instead, we used the pentyl group. So that is the difference between our compound and their compound. And then my PhD student have managed to get 1 gram of this compound. Then we fabricate to make a device, and then it showed that some properties as an OLED. And then we published this finding in Journal of Luminescence in 2017. So this is the main issue with the OLED. We want to make sure that the molecule still have high triplet energy. So we make a comparison. So if we have this molecule, we can see that the triplet energy is around 2.79 electron volt. If we have more longer bridge like this biphenyl here, so you can see that the triplet energy drop a little bit to 2.65, so meaning that this is not good. If we have something to block the rotation here, like introducing this methyl group here, then we see that the triplet energy is maintained at high level, not much different from the triplet energy of the carbazole. So that's why these molecules are good. And then if we have this kind of structure, you can see also the triplet energy is maintained, okay, similar to this one. So this is the whole idea why carbazole is good in this OLED study, because we can functionalize the carbazole at the same time we maintain the molecule at high level of triplet energy, because in the OLED study, one of the good criteria or one of the important criteria is to have the molecule at high triplet energy. This is in order to get blue light, okay, from the OLED device. And then other than that, we also have successfully synthesized this compound, just that we don't have enough amount to do device for this molecule to study their behavior as a OLED device. This molecule also have quite good triplet energy, 2.72 electron volt, which is maybe suitable as electron transport layer or maybe suitable as the host layer in the OLED device. So I think maybe I'm running out of time. So I just would like to acknowledge a few people. I don't know why my slide suddenly become like this. to the KTU where I'm now. Now I'm at the moment I'm in Lithuania at the KTU Technology University under Horizon Mega 2020 secondment. And also I would like to thank University Malaya for various grant that I received, and also the Ministry of Higher Education for the FRGS grant, Ministry of Science for the Science Fund, and also one company that initially sponsored us to start this OLED study. Thank you for your attention. So if you have any question, you can.
Okay, thank you very much, Prof. Dr. Azhar, for addressing the interesting keynote speech on carbazole-based dendrimers in OLED applications. So, ladies and gentlemen, now we come to a Q&A session. I will read the question from the QA banner. So, the first question is from our Dr. Nor Alia. Assalamualaikum, Prof. Azhar. Thank you for your great sharing. May we get opinion on the production cost of OLED, since it has been reported to be rather higher than LED?
Okay, thank you for the question. I'm not in the business line to give an accurate answer. So the answer is yes and no. It depends on which aspect that you look. If you look at the big screen of OLED, yes, the production cost is still high. But if you look at the small size like our handphone here, so we have been using this, is it expensive? So I think even the student can afford to buy the smartphones. No, so meaning that for the small size like the handphone, the cost is not that expensive. But for big screen like OLED, LG, they have LG OLED TV now. That one is maybe expensive, and also the reliability is still not there if we were to compare with LED. Yeah, that is true. In certain aspect, LED is still better than the OLED. But if you look at the small size of the device, yeah, OLED is better in certain aspect. So there is pro and con, and that is why research in OLED is still ongoing. Many people still doing research. If you look in the publication from China, from Korea, from Japan, there is a lot of research still ongoing, because we still try to get a big screen OLED with cheaper, but at the moment still not there, and also the reliability is still not there for big screen. But for small screen like handphone, I think there should not be any problem, because everybody is using the OLED device now in their hand now. I hope I answered the question.
Okay. Thank you, Prof, for your answer. Now we're moving towards to the next question. So the next question is from Dr. Tan. Good day, Prof. Azhar. OLED has excellent viewing experience, but he has a shorter lifespan than LED, right?
Yes, the answer is right. For big screen, for small screen, I'm not very sure. Because I've been using my smartphone since 2018, and until now it's still working. But yeah, I cannot give you the exact answer, but I just based on my experience. Yes, the answer is right. LED is still better for big screen. But small screen, I think LED and OLED, I think they are comparable at the moment. That is my answer.
Thank you, Prof. We have a next question for you from Madam Shabila Sazali. Assalamualaikum, Prof. Such an interesting presentation. May I know, does molecular weight of the compounds give effects on its efficiency?
Okay, actually the molecular weight does not give much effect on the efficiency, but the design is important. So one of the reason that I choose carbazole, because from my understanding, I'm not actually a physicist, I'm a synthetic organic chemist, but I try to understand the basic concept that is required in this OLED business. One of the criteria is what I understand, we need the molecule to have high triplet energy. So the main concern is whether the molecule can have high triplet energy or not. So either the molecule small or big, that one does not affect the efficiency of the device. The purity of the compound is the main, the other important thing. So the design of the structure and the purity of the compound when we make the device is the important. That is the thing that will affect the efficiency of the device. But the size of the molecule not, because in our case, our molecule size is 1,500 gram per mole. That is the smallest that we have. We also have molecule size of 2,000 gram per mole. So this is what, if we're talking about not a polymer, because I think maybe in the market now, maybe they use polymer. I'm not sure, because this Samsung or this digital company, they keep secret, so we don't know what is actually that molecule that they use. But they use organic molecule, but we don't know. I don't know whether they use a polymer kind of organic molecule or they use a small molecule. But to answer that question, in my opinion, the size of the molecule will not affect the efficiency, but the design of the molecule will affect whether the molecule have high triplet energy or low triplet energy. That's from my understanding as a synthetic chemist.
Thank you, Prof. Thank you for the answer. Now we have a last question from Mr. Iman. Thanks, Prof, for the interesting topic. Regarding to the OLED, they have some toxicity to a people's and maybe environment. Can you explain a bit about the toxicity from it by comparing with LED perspective?
Okay. Now we are talking about organic molecule versus heavy metal. Okay, in the first place when OLED was introduced, they are using heavy metal like iridium for the emitter layer. So, and then slowly we replace the iridium with the organic material, because iridium is heavy metal, it's difficult to get, and then the cost is very high, and it also toxic. So LED, from my understanding, for the semiconductor, the doped semiconductor, they are using metal. For example, gallium. But I don't know, gallium, is it toxic or not? But to be honest, all organic molecule, all chemical, we can call it toxic, but it depends on which aspect that you look at it. So if you're dealing with chemical, you cannot avoid from having this toxic thing. But as far as I'm concerned, the molecule that we make ourselves in the lab, Carbazole, for example, Carbazole is not toxic at all. It's a nice yellowish powder. You can play in the round. We have a kilogram of that Carbazole in our lab. But when we make it into device, I'm not sure, because we have electrode which is made of metal like aluminium. So aluminium, you want to talk about toxic, aluminium is also toxic. So in the LED, they have a lot of metal inside there, so which is also toxic. So I cannot give exact answer here. I think both have their pro and con in terms of the toxicity effect. So that is the honest answer that I can offer.
Okay, thank you, Prof. Thank you for the answer. Thank you so much for your significant sharing of today's speech. So now we reach at the end of this session. Thank you all for your participations. And on behalf of the MICNC 2021 Organizing Committee, I would like to seek for your kind cooperation to fill up the feedback form in the chat box. Also, you are invited to join the rest of the event after the lunch break. Please join us again at 2 p.m. for more interactive parallel sessions by our speakers. Hope to see you again. Thank you very much for your time and support. Thank you all.